We routinely mistake high-stimulation environments for advanced learning. Modern synchronous virtual classrooms are dense with competing stimuli, requiring users to navigate video feeds, chat boxes, whiteboards, and screen sharing all at once. The financial commitment to these environments is massive. By 2022, e-learning accounted for up to 70%. The core failure lies in prioritization. Instructional designers build massive digital infrastructure to deliver data, but routinely ignore the biological hardware receiving it. If we want a return on our training investments, we must stop evaluating platforms by technical specifications and start measuring their invisible cognitive footprint. The human mind does not operate like a hard drive. It does not passively accept file transfers or download presentation decks into memory. Learning is an active, taxing process of knowledge construction. This maps the cognitive pipeline. Information enters visual and auditory pathways, converging into working memory. With a strict capacity limit, it quickly overflows. Without active processing, data evaporates in 20 seconds. Learning only happens when this volatile data integrates into long-term memory. Because working memory is minuscule and highly unstable, overwhelming it guarantees the learner loses the data before integration occurs. The entire training module becomes useless. Instructional designers must manage this limited bandwidth like a triage unit. As we see in this framework, cognitive load theory divides mental capacity into 3 competing allocations. The system is strictly zero-sum. The first allocation is extraneous load. This is mental effort wasted on poor interfaces, visual searches, or irrelevant graphics and background sounds. Look at this layout explaining a complex physical process. The visual of the lightning formation is centered, but vertical separation forces the learner into an artificial visual search task. Scanning back and forth across the empty space drives extraneous processing load dangerously high, consuming the user's limited bandwidth. The engineering solution is the continuity principle. Placing the explanatory text directly adjacent to its corresponding graphic eliminates the visual search instantly. Any design choice that does not directly support the core lesson is noise. We must aggressively minimize extraneous load to create space in working memory for actual sense-making. The second allocation is essential load. This is the baseline mental effort required to hold and understand the core concepts of the subject matter. It is dictated entirely by the natural complexity of the topic. You cannot delete essential complexity without dumbing down the material. This graphic illustrates an unbroken flow of continuous data. If delivered all at once, this mass of information immediately crashes the learner's processing capacity. To fix this, we apply the segmenting principle. We break the continuous lesson into smaller logical chunks, providing the user with a next button. Surrendering tempo control to the learner acts as a required safety valve. It allows working memory to process one conceptual step fully before it is forced to accept the next. The final allocation is generative load. This is the deep, active cognitive work the brain performs to organize material, build mental models, and integrate new facts with existing knowledge. Generative work relies entirely on the biological architecture we established earlier. The brain processes incoming stimuli through completely independent parallel pipelines for the eyes and the ears. This schematic visualizes the traffic jam created by poor design. When instructional designers force learners to read dense on-screen text while simultaneously watching a complex animation, both streams of data collide inside the single visual channel, overloading the pipeline. To bypass this visual bottleneck, designers use the modality principle. By migrating the explanatory text off the screen and into an audio voiceover, the data flow is instantly balanced across both sensory channels. The eyes process the graphic, while the ears process the words. Balancing the dual channels protects working memory from systemic overflow. It is the ultimate catalyst for generative processing, freeing the brain to fully encode the knowledge. Evidence-based design carries a critical boundary condition. Techniques that work perfectly to support learning in one scenario can actively harm it in another. This interface slider demonstrates the strict scaffolding, step-by-step pacing, and visual pointers required for an absolute novice. They need these guardrails to form their initial mental models, but as a user gains proficiency, their cognitive needs invert. This is known as the expertise reversal effect. Experts already possess internal mental schemas. Forcing them to sit through heavily narrated, step-by-step modules creates frustrating extraneous load, blocking them from the complex tasks they are ready to perform. These principles are not intuitive preferences or stylistic choices. They are established metrics backed by decades of randomized controlled trials and massive effect sizes. Digital architectures must adapt to the prior knowledge of the user. If they do not, the interface itself becomes a biological barrier to execution. This flowchart synthesizes these biological rules into a single, definitive architecture for digital instruction. It moves linearly from clearing visual noise to balancing the sensory channels, segmenting the pace, and finally, demanding generative practice. Instructional designers frequently fight stakeholder demands for flashy, overloaded training modules. To win those fights, we have to stop arguing about aesthetics and start pushing back using the indisputable metrics of cognitive load. The core operational rule is this: if a new feature, platform, or animation does not actively foster generative processing or pace essential complexity, it must be aggressively cut. We must build environments that respect the severe biological limitations of the human mind. The most effective digital learning environment leaves zero technological footprint. It simply clears the pathway for human knowledge construction.